Good day everyone, my name is Leslie Pearl Echnaldo and I am here to report to you the Unit 7 which is the densities and porosities. To start off, volume and mass relationship of soils. Volume composition of soils. Where are the components are the mineral matter that has 45%, organic matter has 5%, soil water has 25%, and soil air has 25%. Both mineral matter and organic matter are solid, and its soil fraction is solid fraction of 50%. Meanwhile, the soil water is liquid and soil air is gas, and its soil fraction are the pore space of 50%. Volume and mass parameters. The parameters presented in Figure 10 is important in determining the density and porosity of the soil, where V is volume, VA is volume of air, VW is volume of water, VF or VP is volume of pore space, VS is volume of solids, and VT is total volume of soil. M stands for mass, MA stands for mass of air, MW is mass of water, MS is mass of solid, and MT is total mass of soil. So we have here the illustration of figure 10, volume and mass parameters, where the volume of pore space is equals to volume of air plus volume of water. Total volume of soil is equal to volume of pore space plus volume of solid, or total volume of soil is equal to volume of air plus volume of water plus volume of solids. In mass, total mass of soil is equal to mass of air plus mass of water plus mass of solid. Another is mass of air is equals to 0. Therefore, total mass of solid or total mass of soil is equal to mass of water plus mass of solid. For a given amount of soil, mass is the oven dried weight of the soil which dry up in the oven at 105 to 110 Celsius for at least 24 hours. A moisture-free soil or the mass of the soil solid alone. Volume. There's two values are possible. Number one is the particle volume. Vs or the volume of soil particles or the soil solid alone, and bulk density or the Vt means total volume of soil, or other words the volume of solid and volume of pore space. There are two densities of soil depending on which of the volumes is used. Particle density if the volume of solid is used, and the bulk density is if the total volume of soil is used. So we have here the bulk density. Bulk density of the soil is the mass or dried weight per unit volume of soil, a measure of degree of compaction of the soil, an indicator of the soil porosity, an indicator of soil structure. The more compact the soil, the greater is the bulk density value and the less porous it is. Mathematically, bulk density is determined by the formula where BD or BP is bulk density, MS is mass of dry soil, and VT is total volume of the soil. So we have here the range of bulk density values for sand and sandy loam soil is 1.20 to 1.80 grams cubic centimeters, while for clay loam and silt loam, the bulk density usually ranges from 1.0 to 1.6 grams cubic centimeters. The optimum bulk density of soil is 1.30 grams cubic centimeters. However, bulk density does not remain constant for a given soil. Factors affecting bulk densities. Organic matter content. Bulk density decreases with increasing organic matter content. Soil texture. The coarser the texture, the higher the bulk density, and the finer the soil, the lower the bulk density. Tillage practice may increase or decrease bulk density. Number 1. Granular structure or pore use have low bulk density. And number 2. Compact soil results in reduced pore space and high bulk densities. Portion of the soil in the profile or soil depth. Soil layer in the top have low bulk density, and bulk density increases as the layer of the soil increase. Soil porosity. Bulk density decreases with increasing porosity of the soil. General characteristic of soil with low and high bulk densities. Soil with low bulk densities, rapid infiltration and percolation of water, adequate water retention due to their high organic matter content, highly permeable. Permeable soil allows ready penetration of air, water, and plant roots, well drained and well aerated. Soil with high bulk densities. High bulk densities values are greater than 1.6 grams cubic centimeters, limited soil aeration, very slow water movement, poor drainage, recent root growth in the soil. Sample bulk density computation. Problem. The mass of soil solid is 150 grams and the total volume of soil solid is 100 cubic centimeters. So the given are the mass of soil is 150 grams and the total volume of soil solid is 100 cubic centimeters. Therefore, the formula of this is bulk density is equals to mass of soil solid divided by total volume of soil solid, which are the 150 grams divided by 100 cubic centimeters is equals to 1.50 grams per cubic centimeters. So we have here the particle density, refers to the mass or dry weight per unit volume of soil solid alone, excluding the pore spaces within the soil volume. Mathematically, particle density is determined by the formula where PD or double P is the particle density, MS is the mass of dry soil or oven dried weight, and VC is the volume of soil solid. Particle density of most mineral soils usually varies within a narrow ranges of 2.60 to 275 grams per cubic centimeters. Factors affecting particle densities. A. 2.65 grams per cubic centimeters is the average particle density. B. Organic matter content. The greater the organic matter content, the lower the particle density values. The low particle densities or soil is a high in humus. So soils with high organic matter has low particle density. The particle density of organic matter is 1.20 to 1.50 grams per cubic centimeters. Organic matter generally higher in topsoil than subsoil. Surface soil have usually lower particle density. Mineralogical composition. Heavy minerals tend to have higher particle density values. High particle density soils derived from heavy minerals like iron-bearing minerals. Sample particle density computation. Problem. The mass of soil solid is 150 grams and the volume of soil solid is 60 cubic centimeters. So the given of this is the mass of soil solid is 150 grams and the volume of soil solid is 60 cubic centimeters. Therefore, the formula of this is particle density is equals to mass of soil solid divided by volume of soil solid, which result like this: the 150 grams divided by 60 cubic centimeters is equals to 2.50 grams per cubic centimeters. So we have the soil porosity. The amount of free space in the soil is given by the total porosity, which is defined as the proportion of the total pore space volume to the bulk or total volume of soil. The pore space is the option of the soil not occupied by the solid components and filled up by water and gases. Mathematically, porosity is determined by the formula where Ps is pore space or porosity, Vf is the volume of pore space, and Vt is bulk or total volume of soil. A solid has two major fractions, the solid and the pore space fraction. The solid fraction is calculated as the ratio of bulk density to the particle density multiplied by 100 gives the percentage of the soil volume that is occupied by the soil solid. So this is the formula. The solid fraction is equals to the volume of solid divided by total volume of soil times 100, or the bulk density is divided to particle density times 100. Since pore space fraction and the solid fraction make up the total soil volume or VT, then the pore space fraction is equals to 100 minus the solid fractions. And since the solid fraction is the ratio of bulk densities or BD to particle density or PD multiplied by 100. So this is the formula. The pore space is equals to 100 minus the bulk density is divided by to the particle density and times 100. Or the pore space fraction is equals to the 1 minus bulk densities divided by particle density times 100. So we have here the classification of pore spaces. A, coarse or large pores. They accommodate gases in the soil, allow passage of excess water, gaseous exchange in the atmosphere, or the soil aeration, and provide space for plant roots. These are pores whose width are larger than the 10 micrometers is equals to 0.001 centimeter. B. Medium pores retain water enough for plants to take up and act as storage for the available water. These are pores whose width ranging from 0.2 to 10 micrometers. And C. Fine or small pores retain water very strongly, and the width of these pores are smaller than the 0.2 micrometers. A desirable pore size distribution in soil is one where the total pore volume is approximately divided equally between the coarse, medium, and fine pores. So we have here the relationship among bulk density, particle density, and the porosity in soil. The higher the bulk density of soil, the lower its porosity. As the BD value approaches the value of PD, the percentage porosity approaches 0. So let's take the example. Assume two soils A and B have the same particle density of 2.65 grams per cubic centimeters. The BD of soil A is 1.50 grams per cubic centimeter, while the BD of soil B is 4.75 grams per cubic centimeters. So In soil A, we have here. Um, so let's just proceed to calculate them. Uh, so 1 minus 1.50 divided by 2.65 times 100 is equals to 1 minus 0.57 times 100 is equals to the 43%. While in soil B, so we have here that 1 minus 4.75 divided by 2.65 times 100. So let's just bring down 1 minus 0.66 times 100. So the answer of this is 34%. So we have the void ratio. The volume of soil pore space, or VF, is known as void. The ratio of the total void volume to the volume of soil solids, or VS, defines the term void ratio, or E. The relationship is given as when E is equals to VF divided by VS, or E is equals to PD divided by BD minus 1, or E is equals to the pore space fraction and the solid fraction. If the void ratio is equal to 1, then the volume of pore space is equals to the volume of solid. If void ratio is lower than 1, then the volume of soil pore space is lower than the volume of solid. If void ratio is greater than 1, then the volume of soil pore space is greater than volume of solid. So let's take the sample computation. The problem is a 100 cubic centimeters soil weight in 160 grams when moist. After oven drying, its weight was reduced to 130 grams. Assuming that the volume of pore space is 50, calculate the following: A. Bulk densities, B. Pore space, C. Solid fraction, D. Particle density, and E is the void ratio. So the givens are: the total volume of soil is 100 cubic centimeters. The mass of water plus mass of solid is equals to the 160 grams when which is the moist soil, and the mass of solid is 130 grams, which is the oven dried soil, and the volume of pore space is 50. So let's take the bulk densities. So BD is equals to MS divided by VT is equals to 130 divided by 100 is equals to 1.30 grams per cubic centimeters. In B, pore space fraction. So the pore space fraction is equals to the VF divided by VT times 100 is equals to 50 divided by 100 times 100 is equals to 50%. While in soil fraction, the pore space is equals to 100 minus the soil fraction, or the soil fraction is equals to the VS and the VT times 100. So we have here the soil fraction is equals to 100 minus the pore space fraction is equals to 100 minus 50 is equals to 50%. And while here the 100 the solid fraction is equals to 50 divided by 100 times 100 is equals to 0.50 times 100 is equals to 50%. Let's proceed to the particle density. The particle density is equals to the ms and vs is equals to 130 divided by 50 is equals to 2.60 grams per cubic centimeters. And we have here the void ratio or E. So here are the formulas. The E is equals to VF divided by VS. E is equals to PD divided by BD minus 1. And we have here the ratio equals to the pore space fraction divided by solid fraction. So in the first formula, we have the 50 divided by 50 is equals 1. And the second formula is we have the 2.60 divided by 1.30 minus 1 is equals 1. And the third formula is we have the 50 divided by 50 is equals 1. So if the ratio is equals to 1, then a solid is ideal. And that will be all. Thank you.